Hi, welcome to SFO15-307, Advanced Toolchain Usage Parts 5 and 6. Today's presenters will be me, Ryan Arnold, the Linaro Toolchain Engineering Manager, Maxim Kuvyrkov, Tech Lead, and Adhemerval Zanella, Toolchain Engineer. So this is a continuation of a series we've been doing for the last few connects on Toolchain Black Magic. We'll be doing a session now and then a session immediately afterward after a break. So parts 5 and 6 are this connect. Parts 1 and 2 and 3 and 4 you can find on SlideShare. So can you go to the next slide? So there's links to parts 1 and 3, but that slide deck for 1 contains 1 and 2, and 3 contains 3 and 4. So we're adding 5 and 6 this time. I'm sure we'll have probably 7 and 8 at a further connect. It seems to be a pretty popular topic. So for suggestions for future topics, please feel free to send an email to Linaro Toolchain, our mailing list, at linaro.org. So parts 5 and 6 are going to cover a variety of topics. Some of these are library-based, and then there's a few compiler-based topics as well. I will be speaking about search paths. Adhemerval will be speaking about symbol versioning, timers, timestamps, and the VDSO. And I believe Maxim's speaking about what the compiler can't know and in-order versus out-of-order execution and what it means to application developers and library developers. So we'll start out with search paths. So before I get there, I want to ask a question. So who can tell me what a static linker is? All right, Maxim?
I'm supposed to answer. Static linker is a utility which accepts object files on its input and combines them into a single object file on the output. Usually the output is either executable or dynamic library, but it can also be just another object file, which can then later be again linked.
Okay, so what's a dynamic linker? Well, it's written here. This loads libraries, resolves symbols in those remote libraries, resolves a few remaining relocations, and it does all of these at runtime. There's a few other things. So Maxim was correct on the static linker. It also defines section layouts. And some of the other things your dynamic linker does is it faults sections into memory, manages multiple instances of the library at runtime, sets read, write, execute permissions on sections. Pretty much, these are two parts of a similar topic, but they have distinct responsibilities. And that matters as we go into the topic of search paths. So that's why I wanted to bring that up first. We're going to be talking about link editors and linkers versus loaders and dynamic linkers. So just be aware that there's some similar terminology. All right, so the term search paths. There's not a good way to give a solid definition, but the best way to think about this is that this refers to how the dynamic linker searches for dependencies at runtime in the form of shared objects. So you can see how the dynamic linker searches or where it searches using an environment variable LDDebug, and you can set libs. There's other ways, other information you can get from LDDebug, but for the purpose of this discussion, if you put libs there and you run your executable, the dynamic linker will spit out the search paths that it's been searching for your library dependencies. I don't have an example of the output. It's pretty simple. It just says, searching for this shared object at these directories, and it'll go through the list. Yes.
What will happen if I do export LDDebug equals libs in my shell?
I would not do that because you will probably get the dynamic linker executing the search paths on shell invocations for bash. So you're probably not going to get the information you think you're getting. I guess I haven't tried it, but that's what I would expect. So obviously the static linker has to either encode paths at link time, or the dynamic linker has to have an implicit understanding of where to find libraries at runtime. So that's, the reality is it's a combination of both. So we have the dynamic linker search order. Very briefly, this is the simplistic view. Most of you probably heard of LDRunPath. That seems to be the thing everybody goes for. We're going to discuss why that's a bad idea in general. So what you haven't probably heard of, or might not have heard of, is RPath and RunPath. They're not new. They're old technologies. They've been around a long time, but they solve some problems, which we'll address. So this is the general order. Pre-linking basically circumvents searching entirely. RPath is a way of encoding the paths in the executable or shared object. Library path, of course, it gives a user override environment variable. RunPath is another way of encoding. And then the dynamic linker will default to what is the ld.so cache, and then finally implicit based library directories. So glibc or the loader will know, hey, look in lib, look in user lib. And usually those implicit paths are defined by how the Linux distribution configures the libdir and slibdir. All right, so let me see. So the best way to describe all of this is via an example, because it's not as simple as this. It's not just as simple as, saying, hey, I've got an executable that's calling a shared object, which developing another shared object, and if I just set the library path, it's all going to work fine. That does not happen. So we'll go to the next slide. So we have a setup. So I'm not even going to show you some real code on this one. This is just trivial. We have a C file, foo.c, calls a function bar. Bar is in libbar.so. Foo is in my home directory, and bar is in a secondary directory. For the purpose of the examples, I could put bar in the local or in the home directory, but you might make some assumptions about what the loader can and can't know if it was in the home directory. So we're putting it in a secondary directory just to explicitly take a look at what the dynamic linker can and cannot know. All right, so going on to the next slide. So we need to tell the static linker where to find libbar.so so we can bind symbol versions and resolve some outstanding relocations. So if you don't tell the static linker where to find libbar, you'll get errors. So everyone's seen this. You see it all the time. Like, oh, forgot to tell it where the shared libraries are. Sometimes your compiler knows where some of its shared libraries are. So if you're linking libpthread, for instance, you could put lpthread without telling the dynamic linker where it is, and the system generally knows where that is. But if you have mylibrary.so, it's not going to know that, and you need to tell it. Yes?
So when a library is compiled, especially if I do my own library, I will often get libbar.so and libbar.a, right? If I put both of those into the same directory, and one is static library, the other one is dynamic library, how the linker will pick?
So the linker picks between .o or .so and .a based upon whether you use the static flag or not. Dash static tells the linker link in the static archive statically. So it'll pick up the static archive that way. And .so is actually a bit deceptive. When you tell the linker to find a .so, what you're telling it is find a linker script. You're not telling it to find a shared object. You're telling it find a linker script which tells me how to find the shared object. But often they're just an alias for each other. But just be aware that sometimes your .so is actually a linker script and not a shared object. Yeah. Look at libc.so. It's actually a linker script to libc.so.6. All right, so since shared library is in libs, we need to tell the dynamic linker where to find this. Oh, wait, can you back up? -L. The compiler forwards that to the linker and says, libbar is going to be in the libs directory. So now we have the executable linked, and it should work when we try to execute it. but it doesn't. And it doesn't because home ryan-arn libs is not in the default search path for the system. It's not in ld.so.cache, and it's not in user, and it's not in lib. It's somewhere else. So the dynamic linker tells us we can't find this shared object. That's because we only told the linker where to find the object for linking, but we didn't tell it how to find, we didn't tell the dynamic linker how to find the object for execution and loading. So the way that a lot of people solve this is using LDLibraryPath. So what this does is tells the dynamic linker at runtime, look in this directory for libraries. So you'll notice I did this. A lot of times, if you just did this part and you left off the back, if you're running in an environment which makes assumptions about LDLibraryPath or has used it before, if you just put the first part and you override it, you're going to mess up every other executable in that dependency chain. So oftentimes, if you leave off the back part, bash will just die on you. Maxim?
Is there a caveat with that particular export LDLibraryPath format?
Such as?
Such as colon at the end, if the LDLibraryPath is empty. That will cause DynamicLinker to look in the current directory too.
Oh, that's interesting. I wasn't aware of that.
So check if LDLibraryPath is empty, and if it's empty, then just set it to the first part without the colon.
You can use bash variable substitution there to only put the colon in if it's not empty. That's probably a better way to do it. So as I said before, there's problems with this LDLibraryPath. Relying on that is a support nightmare. So does anyone know why that's a support nightmare? Any ideas? So when you put this in the hands of the user, you can break the implicit assumptions made by library developers about where those dependencies are located. So if a user does this, and then you get a support ticket, and they say, this isn't working, your toolchain's broken, well, if they've been overriding the library paths, they're breaking all the assumptions about your product. And really, this is not the way you want. You don't want to be dealing with these sort of support issues. And also, as a library developer, you don't want to have to rely on a wrapper script to set LDLibraryPath in order to make your libraries usable. So is there a way to embed the path of the library dependencies in the shared object? Obviously, yes. That's the purpose of the presentation. That's what RPath's for. So this is a dynamic array tag. So this is part of the ELF ABI. And this is information that's encoded in your shared object or executable. So the linker understands RPath. This has been around for 25 or more years. And this is a way to get around having to use LDLibraryPath. You tell the linker, this is where the libraries will be at runtime. And hopefully, your Linux distribution has actually put them there, or you have actually put them there when your installer installs the application. So what does this mean? Libraries in a fixed location can have the path embedded in the shared object, so the dynamic linker knows where to find them. So let's use it in one of our examples. So go to the next slide, please. So that's how we use it, $WL, tell the dynamic linker where to find it. And then if we look at the headers, the ELF headers, we'll see, yes, the RPath, there is an RPath dynamic tag with an embedded path in it. So this is useful for you if your product builds several shared libraries and you know ahead of time where they're located. So what's the issue with this? Can anybody see a problem with this? So the path is absolute, which is suboptimal. So is there an alternative? There is. Use origin. I believe most dynamic linkers, Unix dynamic linkers support this. So origin tells the dynamic linker wherever the executable is located is where origin is. So now you can embed an RPath to origin libs, and the dynamic linker will look relative to the executable for the shared objects.
Just a comment for those who are not fluent in shell. Make sure single quotes are very significant in $origin.
Yes, otherwise origin will expand out to whatever origin is at the time when you executed the link.
Which most likely be empty, and you'll get just /libs. Also, there is a small typo, -o full is meant actually to be probably -o hello, right? If you obj dump hello.
Yes, I went back and changed. I changed slides and I forgot that one. So let me.
So it's the same output binary name.
There. Wait. Oh, it didn't update in presentation mode. Okay. Next slide. LDRunPath, this is the same thing as RPath, but you can set it with an environment variable. I'm really not going to go into it, but this you can do the exact same thing. This just, once again, this is only understood by the static linker and not the dynamic linker. This is the same as using -rpath. So this is not a runtime execution environment variable. If you put that on, if you export that, it won't have any effect at runtime. I don't really know the use cases for this, but it's functionally equivalent to RPath. So I don't know if, does anyone know exactly why you'd need to use an environment variable versus a direct linker flag? Well, I suppose in some cases you don't necessarily have control over, over the linker flags that you're passing. Okay, so next slide. All right, so what if you link RPath and use...
Ryan, sorry, one question.
Yes.
Do you know if these static linker flags or variables are supported by Gold? Or if it's only a BFD linker?
I would assume that these are supported by Gold. And I actually saw a bug report in bin utils about supporting new D tags in Gold, so yes. Okay, next slide. So what if we use RPath and LD library path? So what's going to happen is LD library path is going to be ignored. So as before I said, LD library path is a bad idea, but actually sometimes you need it. Sometimes the user wants to be able to override. So if you use RPath and then you try to use LD library path, the user does, it's not going to work. So there's got to be a solution for this problem. So go to the next slide. This is where DT_RunPath comes in. So this is the new dynamic tag, new D tag. So since the user can't override RPath, RunPath was designed as an alternative. So if we went all the way back in the slides and we looked at the search order, we saw RPath, LD library path, RunPath. What this means is that this new D tags, this new dynamic tag, RunPath, will actually solve this problem. This will, well, let's go to the next slide. We'll take a look, but what the result is that RunPath will be searched after LD library path. So let's take a look at how this is used. It's used the same way RPath is used. So in fact, you know, the binutils developers reused RPath, and you enable it, the new D tags with enable new D tags. And if you obj dump this, you will see you now have RunPath and you have RPath. Does anyone know why RPath is still in there? Okay, I don't either. I was hoping somebody else did. So it's still there for some reason, even though it's ignored. So there's a very subtle but important property that differs when you use those, and we discussed that. That was, next slide please. That was that LD library path is searched before RunPath. Okay, next slide. So this is just an overview of what we talked about. But one interesting thing. So given that we have RPath, LD library path, and RunPath, you should have everything you need, right? No, wrong. The Alpha ABI has deprecated RPath, so you shouldn't use it, right? Nope, that's wrong too, because it's not that simple. So let's talk about a property called transitivity. So you can read this slide. You can read the definition. With regard to a linker, a dynamic linker, and static linking and search paths, transitivity describes a permissive behavior granted to the dynamic linker. The ABI is saying the dynamic linker is allowed to treat an RPath or a path to a shared object in one shared object. It's allowed to use that path to search for any shared objects. So if you have a sequence of shared objects, which are DL opening other shared objects, if you were to simply tell the first, embed the first RPath in the first shared object, the dynamic linker can search for every other shared object in that at runtime. So that's transitivity. You have this idea that you can apply to the third element what you apply to the first and second and between the second and third. So a non-transitive dynamic array tag does not permit the dynamic linker to do that. So next slide, please. DTRPath is transitive. So here's an example. I won't go into it, but this is a common bin, or this is a bin utils bug a number of years ago, which addressed this. So we have code. We have two shared objects. One DL opens. Main will DL open one of them, which yes, main will DL open libso.1. So let's go to where this is linked. So even because of transitivity, even though we only specify the RPath to dot, current directory, on the executable, the dynamic linker is allowed to look for both libso.2 and libso.1 in the current directory. And of course, we're able to find it, and our application works due to transitivity. Next slide. Unfortunately, RunPath is non-transitive, and this is a snippet from the ELF ABI, the generic ABI. I don't know why, but the dynamic linker is not permitted to inherit the paths from other shared objects.
Maybe that is why you have RPath as well. You were wondering whether
Yes.
why there was RPath and RunPath.
Well, unfortunately, when RunPath is available, the dynamic linker simply ignores RPath. You would think it shouldn't, but it does. There's a number of bugs that are open, and they've been open for a very long time, that I try to address this, but there's no real solution. It's sort of a gap. All right, so next slide. I'm going to show you how this is non-transitive. So we had the same linking we did before, but this time all we're going to do is we're going to re-link the executable to the shared objects. So we enable new dtags, which means we pick up RunPath, and we execute, and there we are. We cannot find libso.2 because the dynamic linker is not allowed to apply the search path that applies to the executable when looking for shared objects. And that's due to the non-transitivity clause in the ABI. Next slide. So what's the solution? LD library path. That's one solution. So what this does is the dynamic linker will then look in LD library path for those shared objects. This, of course, means all the other problems with the library path apply. So we're back to square one. So next slide. So another option is to specify RunPath when linking libso.1, so the directory of libso is embedded in the shared objects dynamic array. So then I go and redo the linking. You only have this luxury if you were the one that compiled this shared object. Otherwise, you don't have much else you can do. So this is why, even though RPath is deprecated, it is not in fact has not in fact gone away, because you still need that functionality, because there's a lot of libraries which were not compiled, were not linked with new dtags. They have not been given an explicit search path. So next slide. So Linux distributions generally get around this problem by installing their packages in the common library directories.
So rolling back to the previous slide, why is enable new D tags not the default?
So it's not the default because if you only used enable new D tags, there is no way for the shared object. If the shared objects don't specify RPath with enable new D tags, there's no way the dynamic linker will know where to find them if they're not in the default search order because of non-transitivity.
So these are only applicable for non-default search paths.
Right, so that's what I was saying. Linux distros get around this, making sure all their libraries are installed, next slide, installed in the common library directories such that the default search path detection eventually picks them up. So third-party library and application developers are usually the ones being bitten by this, and also this affects users of DL Open, so there's a number of issues with Qt, for instance, DL opening libraries, and the topmost executable was compiled or was linked with DT-RunPath, and the previous was linked with the old RPath, and you'll get these issues. So this is why RPath is not deprecated. So I don't have a good solution for you. The point of this was not to say, here's what you should do. The point was to outline, these are the issues, be aware of what they are. So one last bit before I wrap up.
Ryan?
Yes.
Sorry. Is there some discussion or bug open to make DT-RunPath transitive?
No. In general, my understanding is that the generic ABI is very slow moving and is not an active community at this point. So I don't believe those conversations have been had. All right, just next slide. Just to wrap up, ld.so.conf, I really don't think I need to touch on this very much, that you can find a lot of information on this on the internet. One interesting thing is you can tell the dynamic linker to use an alternative cache, but doing this in a library application is not recommended because, once again, it's a support nightmare. And additionally, ldconfig needs to be rerun after new paths are added. If you're going to do this, make sure that when your library installs, you run ldconfig in, as part of your RPM post-install stage. That will get it added and get your cache updated. All right, I've already taken way too much time, so I'm gonna pass on to Adhemerval here. Do you want to present off my slide, off my computer? Okay. All right, and I'll page for you.
No. Okay. Can I change?
Yeah, go ahead.
Okay. Okay. Symbol versioning. Basically, it was created to fix one issue we have with old Unixes, and it resolved by creating another issues that we might face now. So the idea is to create a stable ABI and API. Basically, when you have different versions over the years, and you do not want to rebuild and redeploy your binaries over the time because it might be costly. So the idea is to have one version and provide different ways to build and link your application against the libraries. So the idea is basically bash. I believe it's the next slide. Yeah. So what happens is when you break your API, you need to rebuild your application. That's the first thing you need to do. But the symbol version came up with another idea to avoid this breakage. Basically, you do want to keep a stable API over the releases, and the releases number you're gonna define by yourselves. Basically, You can use different numbers or names, whatever you want. The idea is to let the developer keep the stable ABI, and the simple version is to give the tool to make this make this able. And so, so the scenarios. It only work for DSOs, for the shared libraries. So first scenario that you have, it's you're going to create more symbols. You create more functions. You're going to change the structure layout, the structure size. And by doing that, you need to rebuild your DSO. So that's one scenario that symbol version came up to help the developer work with. Another one is you need to update the DSO without changing the versions. Yes?
What is a DSO?
Oh, sorry. It's a dynamic shared object.
Shared library.
Shared library. So the another scenario is you need to provide update binary, update DSO. You just find a bug fix with a symbol, and you need to recompile it without changing ABI. Okay? And the another one is you have this bug fix, but this bug fix requires the ABI change. You need to change the symbol name or the symbol arguments or the symbol structure, whatever. It will change the function prototype you have already deployed on your DSO. So basically, you're gonna change how you're gonna accomplish, but that's the main scenarios I can think of that symbol version can help you with. So the first example I have, which is with OldSolaris did back when the ELF was created. Basically, you have different shared libraries using file system name schema. So you have one library that has one version with a .o appended, .1 appended on the shared library name. And when you deploy a new version, you just bump up this number and redeploy the shared library and rebuild your application. So what's the problem about this? What's the issues about that? It works well when you have one binary that links against one shared object, but imagine if you have like 30, 40 shared objects different linked against your binary. And each one of these shared objects using different versions of the other shared objects. So you're going to have a very large tree that will have different versions being linked with, and the shared and the DynamicLinker will have a very hard time trying to figure out how to make this happen on the program image. And it might not work depending on how you link against the versions that you have spread across your system. And it's a waste of resource because mainly you're going to have different versions installed on your system. It will increase the disk utilization and might increase the memory utilization as well because you're going to have different memory, different data sets on the program image. So GNU came up with a solution. In fact, Solaris was the one that did the symbol version, but the GNU extended it to provide different versions, which is like a tag appended to the symbol, and the DynamicLinker will check this version and try to come up with a tie when your program is loading by the DynamicLinker. So the idea, for instance, you have two binaries and a DSO that can be updated basically by just replacing the DSO on the file system. You don't need to redeploy the file, the DSO or the binary. I don't know. I have these examples. Should I show? I don't know which is the better way. Do we have time? I don't think so.
Well, we're running late.
Okay. Yeah, I can continue later. So But the first thing you have with versions, which is numbers or some simple tag attached to the symbol, you can, for instance, when you have a new binary that will build against that library, it will use the default symbol. Which is a default symbol? It's basically a symbol that will be used again when you have the new binaries built against it. So the idea is you continue to provide old versions in the same library, but new binaries will be linked against the symbol that you define that will be the correct one, or the one that you want to provide as a default one. Because the idea is instead of have different shared libraries spread across the system, now you're going to grab all the symbols you want to provide and put this together only one shared library.
So I have a question. If I have an application that triggers a bug in the library, now if I just fix the library and make a compatibility symbol there, do I need to rebuild my application?
That really depends of how the ABI will be tied together with your program. If it's just a symbol without that makes no assumption about the variables layout, for instance, you are passing a struct, it makes no assumption about the struct or the return variables, it can't work.
But my from your example, it seems like that all the programs that were previously built against the buggy library will still use the old buggy versions, and will not use the new corrected version.
Yeah, the idea is, it's because the idea is to not break old programs. The old programs are working with the older version, and you're gonna just need to redeploy the old version symbols when you have a bug fix that do not change it as a functionality. Because the idea is, if you have a new functionality for that symbol, it makes something different, then you need to provide another version.
New functionality as in signature, function signature change,
not really.
The underlying code.
I'll give an example that I was working with. There is the...
For example, the side effects of the function.
Yeah, exactly.
The side effects of the function could be different, and it could change the way the application behaves in the long term. So that basically that is essentially an ABI breakage. So only if there is an ABI breakage do you introduce a new version symbol, a new symbol version. Otherwise, you don't.
Yeah.
Otherwise, you continue to use the same default symbol version.
Yeah, I'll give you an example. There is a FMAN open implementation back in GLBC that was not POSIX compliant. It has been created in GLBC and then POSIX has adopted, but POSIX has changed the specification over the years, and GLBC didn't come up with a better solution. So we have this old symbol that some applications depend of that behavior, and when we create a new implementation that should be POSIX compliant, we couldn't make that the default symbol because it will probably break the old programs. So the idea is to provide a new version, updated version, the default one, that will be the one that the new programs are going to use it, but the old ones that rely on this old implementation, they will continue to use that symbol.
So the old symbol is version tag. So when DynamicLinker looks at the needed list in the shared library, it will say, I need hold mem open against this old version of GLBC, applies the version tag to the function to resolve the symbols
Yeah. And I have this, it's basically this example 4, it's basically what we're discussing here. It's to provide, the idea is you have the first version of your program, you have links against a shared library, it provides one version, and then you update that version with new functionality, you change the prototype. For instance, it receiving a struct, and the struct, it has more fields right now, and then you create a not binary, and it will use the new implementation. But the old one we still continue to use the old symbol without any breakage. I forgot to say that all these examples I have updated on the GitHub. It's very small and very simple, just to give the idea how to work with this versioning. They are very simple compiler instructions. They are extensions of GNU. So, there's something here. No, no.
Okay. I disabled Transitivity, sorry.
So we're actually out of time, but we can continue when we get back. Do you want to show the examples when we return?
Yeah.
So why don't we do that?
I believe I have only one more.
Oh, you want to go one more slide? Okay.
Okay, it's just some resources you can check over the internet. The first one is, I believe, the one that's used more extensively to know how this versioning working. It was written by Draper, and he was the one that came up with the GNU solution for symbol versioning. There is the second one is, I believe that Ryan has written this. It's basically when you have a structure change in the ABI, but you don't have the luxury of doing the dynamic linking. You need to do static linking, and you can come up with some solutions to change that. The third one is my examples, and one thing that's very, very nice, I just found out like 6 months ago, it is project named libgale. Basically, it's a program in a set of tools that you can use to check if your library has the same API or ABI, what has changed, how it's gonna it generates graphics and reports to show you how to update your ABI or how you have updated your ABI, and to work with this kind of symbol versioning.
All right, so we'll continue in about 10 minutes, and we'll actually give Adhemerval a chance to show his examples just so you can see what the compiler constructs are, and then we'll move on to the other parts of the presentation. So we'll see you back here in 10 minutes. All right, thank you.